Hello and welcome to the second tutorial. Today we shall be creating the model of a beam structure and analyze it using the FEA. So without further ado, let's begin. The structure of this beam can be found in a PDF file and the link is shared below. So first we go to File, New Model Database with Standard Explicit Model. Next we shall create the part. To create the part, we double click on the parts. We name it frame. It shall be 2D planar, deformable, wire with an approximate size of 6, and we continue. Let us start by creating the structure. So it will be triangular in shape. Let us add more lines. Okay, let us split the lines, and next let us add some constraints. So this and this, so first we have to choose horizontal. This will be horizontal, this will be horizontal. Then we choose vertical. This shall be vertical and this shall be vertical, and then we choose equal length. This and this shall be equal length, and this shall be equal length. Now let us add dimensions. Since there are no units in ABAQUS, we shall be following the SI standard units. So this shall be 2 meters and this shall be 1 meters. Now if you want to double check that the other ones are also the same, you can also try measuring the distance. This is measuring the length, this is 1 meter and this one is 2 meters. So this one satisfies our structure. So here we are done. We can have the structure over here. Next we will be required to create the material. So double click on the materials. Let's name it steel. For this steel we go to mechanical elasticity elastic. The Young's modulus for this one is 210 GPa, so it will be 210 E9 in pascals, 210 into 10 to the power 9 pascals, and the Poisson's ratio shall be 0.25, and we continue. After the material is done, since it is a beam structure, we will require a profile, the beam cross-sectional profile. So we double click on the profiles. Let us name it circular. So we'll click on circular and continue, and the radius will be in meters, so the radius will be 0.05 meters, and OK. Next we shall be required to create the sections. So to create the sections, we double click on sections. We'll be naming it beam, and we go to beam and select beam and continue with the default settings. Next we will be required to assign the sections. So we go to parts, we go to frame, and we'll double click on section assignments. Select the regions to assign a section. So let us create a set called all and just select all these members and done. Section is beam, region is all, and we select OK. Since the color has changed, means the section has been assigned, and you can also see the section assignment has been changed to 1. Next we can set the beam orientation. We double click here, we click on assign beam orientation, and it asks us to select the regions to assign a beam section orientation. Since we had selected it earlier, we click on sets, so click on all and continue, and you can see it is here. The default value is given. We press enter. You can see OK to input and dismiss. Next, you can see the actual shape or of the model. To do this, you go to view, you go to part display options, and we change the settings to render beam profiles. Apply. So here you can see the kind of 3D shape, actually in 2D, but you will be able to visualize it in 3D. So let us unselect it, apply to continue with our analysis. Next, we shall be required to create an instance for the assembly. So let us hide these. Let us go to assembly, double click on instances, parts frame, and OK. And the frame 1 instance has been created. Next, we are required to create a step. So to create a step, we shall go to steps, double click on steps, and name it apply load. We shall select all the default settings and continue. The default settings will be there as it is, and we shall continue. And the step has been assigned. Next, we will be required to create a boundary condition. So there will be two boundary conditions. It shall be a fixed pin support at the bottom left here, and a roller support at the bottom right over here. So to do so, let us double click on boundary conditions. Let us name it left fixed. Apply load, mechanical, displacement, rotation, and continue. Select in viewport. We select this vertex. Let us name it left and done. We will be selecting constraints in the U1, which is the X direction, and U2, which is the Y direction, and clicking OK. Now you can see the boundary condition is set up. Now let us double click on boundary conditions again. Let us name it right roller, apply load, mechanical, displacement, orientation, continue. We shall be choosing this right vertex, naming it right, and done. Here, since it is a roller, the constraint will only be in the Y direction. So let us just select U2 and OK. And you can see that the roller support has been created on the right. Next, we shall be required to apply a load. So to apply a load, let us double click on the loads. We shall name it line load. The step will be apply load, mechanical, line load, and continue. So we need to select where it will be applied. So we shall select this member and this member. Let us not create a set now, and done. So component 1 is in the X direction. Since it is 40 kilonewton, we shall apply 40,000. So it will be 40,000 Newton, and click OK. And here you can see that a line load of 40,000 newtons in the X direction or U1 direction has been created. Next, we shall be required to create a mesh. So to create a mesh, we go to frame, double click on the mesh, then we go to mesh, element type, click on all, continue, standard, beam, linear, and OK, and dismiss. Then we go to seed, part. We shall choose an approximate global size of 0.5, apply, and select OK. Then we shall go to mesh and part. OK to mesh the part, and yes, and you can see the part has been meshed. the view had been toggled on under part display options. So here, if you just want to see the nodal labels apply, so you can see just the nodes, or if you want to see the element labels, you can see only the element numbers. If you want to see both, you can see both, and for now we shall toggle off. Apply. OK. Next, we shall be required to create jobs. So we go down to the jobs section, double click on jobs. We shall name the job frame 1. Let us just name it frame, and we'll select continue. We'll select all the basic default settings and continue. Next, we'll right click on jobs, and we will go to under jobs, right click on frame and select submit, and we click OK. And you can see that the job frame has been completed successfully. Next, you would like to see the results, so right click on the frame and click on results. Here you can see the original shape. Let us go and remove this information. So we go to options, common, not this. So we go to, we will go to the viewport annotation options, and remove these three: title block, state block, and show text and arrows. Apply and OK. So you can see the undeformed shape. This is the deformed shape. The deformed shape is looking a bit funny. So if you would like to change the dimensions, we go to options, common, not the dimension, the scaling factor. Let us go to uniform and select 1 instead of the auto compute value of 1676.9751, and apply and OK. And here you can see that the deformed shape is not actually visible to us. Next, if you'd like to view the contour plot or the von Mises stress plot, you can click on plot contours on deformed shape. Let us move this, and you can see that the value is 7.672 10 to the power 7 pascals. Next, if you'd like to find the value at any of the nodes, we can go to probe. Next, let us show the boundary conditions. So we go to view, ODB display options, go to entity display, show boundary conditions, and apply and OK. Next, if you would like to find the forces in the X or Y direction at either supports, we go to RF reaction forces. Let us choose RF1, meaning force in the X direction, and then we go to tools, query, select probe values, and select nodes from here. So when we go here, you can see the force in the X direction is minus 80,000, meaning the force is actually to the left, 80,000 Newton to the left. And if you go to the other support, you can see that there are no forces in the X direction. Now if you toggle this one to RF2, meaning force in the Y direction, you can see at this one the force is minus 20,000 newtons, and at the other nodes it is 20,000 newtons. Next, if you'd like to find the horizontal displacement in this at point C, we can go to U, and go to U1 is in the X direction. Again, click on probe values, and then when you hover your mouse over at point C, you can see the value over here. Or if you want in the other direction, you can hover it over here and you can see the value it mentions over here when you hover over the point C. Let us cancel it. Now let us just go back to the model, and suppose we are required to change this roller support to a fixed support. So what we have to do is we have to go to BC, right click on the roller, edit, and add the constraint in the X direction as well, and OK. And here you can see the constraint is added. Now we will create a new job. Let us name it frame 1 per se frame 2 and continue, and OK. So here we have frame 2. Let us submit this job. Submit. OK. The job is currently running and the job is completed. Right click here and click on results. Here let us go to contour plot. You can see the value is almost similar, and if you would like to change, and if okay, let us just move it. If you would like to change this viewing factor, scaling factor, go to options, common, change this value to 5, apply. You can see some subtle differences over here. Okay, if you want to go to the deformed shape, plot deformed shape, you can see this deformed shape with a scale factor of 5. Again, if you would like to probe the values for forces in the X and Y direction, we go to RF, then we go to tools, query, and probe values, select nodes, and here let us RF1 in the X direction. So you can see the force in the X direction is of this value under here, and the force of X direction at the second support is here. It is different than the previous one since the support has been changed. Next, if you are looking for forces in the Y direction, you can see the values over here. Again, if you are looking for the displacement values in the X direction, perhaps at this point C, you can see the value here. It is 0.000119494, or you can choose to see the value in the Y direction to be about 2.11499 e power minus 5. These all values are in meters. Next, if you'd like to see the von Mises maximum value, you can see it over here for this one, or you can check it with the results from the previous data. So here the value will be 7.672, which is slightly different because of the changes in the boundary condition or the change in the different supports. So that is how you complete this beam lab. Thank you everyone. Hope you enjoyed this video.